Comparative study of flyback DC-DC converters. Introduce myself. My name is Nur Nadira Ayuni Maulad Mahmudin and I have been supervised by Dr. Wahida binti Abdul Halim. This video consists of 5 parts, which is introduction, literature review, methodology, result, and conclusion. First part, introduction. Project background. This project is about DC-DC converter. In general, there are two types of DC-DC converter, which is non-isolated and isolated topologies. Non-isolated converter may be constructed from single converter, such as buck converter, boost converter, or buck-boost converter. Meanwhile, isolated converter may be constructed using the flyback converter, forward converter, push-pull converter, or bridge converter topologies. Flyback converter is a transformer isolated version of the buck-boost converter. Flyback converter were commonly used in applications that needed high-frequency voltage signal. Flyback is often used in low-power switch-mode power supplies such as phone chargers and computer standby power supply. Flyback may also be utilized to create a low-cost multiple output power supply with a maximum power of 250 watts. The horizontal deflection drive for cathode ray tube used in television and monitors is often combined with the flyback converter. Flyback converter may also be used to provide high voltage for laser, copiers, and xenon flashlight. Flyback may also be utilized as a gate driver for isolated gate. Next is objective of the project. First, to study the several types of mathematical model of flyback DC-DC converter. Second, to design and analyze flyback DC-DC converter performance using MATLAB and Simulink. Lastly, to validate the performance of the circuit using MATLAB and Simulink. Scope of the project. The flyback type chosen are conventional flyback converter, flyback with RCD snubber, active claim flyback, and interleaf flyback. This project consists only one part, which is modeling simulation using MATLAB and Simulink. For the simulation, these topologies had been tested with various values of duty cycle starting 0.2 up to 0.8 and switching frequency which is 10 kHz and 50 kHz. The flyback design is set to a 24-volt supply voltage in order to produce a 100-volt output voltage. The 100-ohm resistor will act as a load for the output voltage measurement. The chosen switch that will be used in this project is N-type MOSFET. In the end, the output voltage and the converter performance will be observed. Second part, literature review. Literature review will cover 4 types of flyback, which is flyback converter with RCD snubber, active clamp flyback converter, and interleaf flyback converter. This is the basic flyback circuit. The main component consists is input voltage, pulse generator, MOSFET, transformer, diode, output capacitor, and resistor. Flyback converter is a simple switch mode power supply. Flyback converters are designed to allow the power from the input transferred to the output when the MOSFET turned off. Generally, flyback converters used for high voltage and low power application that usually less than 100 watt. Conventional flyback operation mode. When the MOSFET is turned on, the input voltage will be applied to the primary side of the transformer. The DC voltage from the power supply is impressed across the transformer, thereby putting energy into its magnetizing inductance and increasing the magnetizing current. During this time, the secondary side diode is reverse biased and the voltage applied to the diode is equal to the output voltage. The output capacitor provides load current during the on time. It is important to note that the MOSFET and the diode should never conduct at the same time. When the MOSFET turned off, the energy that was stored in the transformer's magnetizing inductance is transferred to the output. Since the MOSFET turned off, the current in the transformer transfers to the secondary and flows through the diode that is now forward biased, replenishing the output capacitor and supplying the load. The secondary side current ramps down as the transformer core demagnetizes. During this MOSFET off time, the primary side is considered an open circuit. Next, this is flyback circuit with RCD snubber. It has additional diode, resistor and capacitor at the primary side compared to the conventional flyback circuit. RCD snubber is categorized in passive clamp. RCD snubber is often referred as RCD clamp due to its ability to clamp voltage spike without altering the spike or ringing frequency. RCD snubber are composed from three components, which is resistor, capacitor and diode. When the MOSFET turns off, a high voltage spike occurs on the drain pin. The excessive voltage on the drain pin may lead to a breakdown and eventually damage the MOSFET. Therefore, it is necessary to add an additional circuit to clamp the voltage. Operation mode for flyback with RCD snubber. When MOSFET is turned off, the voltage rise across the MOSFET is lower as the net capacitance is larger than without RCD circuit. Energy that transferred to the C snubber is transferred to R snubber, which allows C snubber to discharge, so that the voltage across the MOSFET does not become excessive. When the voltage across the main MOSFET exceeds the input voltage, the snubber diode will turn on. It will lead to voltage clamping and leakage inductor current absorption. Snubber capacitance value is chosen large enough such that its voltage does not change during one switching period. This is active clamp flyback converter circuit. It has additional capacitor and auxiliary MOSFET at the primary side. Active clamp flyback converter circuit represent the typical flyback converter topology with auxiliary MOSFET and a capacitor. As a result, the main MOSFET and the auxiliary MOSFET share the leakage energy flow. The voltage stress on the main MOSFET will be reduced, and the DCM mode of operation will be eliminated. The active clamp circuit is used to accomplish zero voltage switching for the primary MOSFET. The switching loss will be considerably reduced as a result. The current stress on MOSFET switches is further increased by active clamping. This is interleaf flyback converter circuit. It has additional transformer, MOSFET and diode. Interleaf flyback converter basically has two flyback converter in one circuit. The continuous conduction mode produces a high DC flux density and demands a big transformer. However, it lowers the power density of the converter. As a result, a flyback converter with two transformers is used, also known as interleaf flyback converter. The DC flux in this flyback transformer is split equally. This will reduce transformer core and copper losses. The load current is balanced between the secondary side of the two transformers using an interleaf flyback converter topology. It also lowers the conduction loss of rectifier diode. Next, methodology. To design the simulation model circuit, we need to calculate the component value. The parameter was set as shown in table to calculate the C output, arc snubber, C snubber, and C claim. The component value were calculated by using this formula. These are the component value that has been calculated. Then the simulation model were constructed in Simulink using this value. All the result and waveform were recorded and tabulated. Part 4. Result and discussion. First part, conventional flyback simulation result. This is an example of the simulation model that has been constructed in MATLAB. This is the result waveform, which is input current, output voltage that been obtained from the simulation. This is the conventional flyback result. When switching frequency 10 kHz, the result was tabulated in black table. When switching frequency is changed to 50 kHz, the result is tabulated in blue table. Then the graph is plotted from the table. On the left side, output voltage versus duty cycle. As you can see, as the duty cycle increase, the output voltage also increase. In the case of switching frequency, when the switching frequency is 50 kHz, it produces higher output voltage than when switching frequency is 10 kHz. On the right side is efficiency versus duty cycle. Same goes to efficiency. As the duty cycle increase, the efficiency also increase. And when switching frequency 50 kHz is produced higher efficiency than switching frequency 10 kHz. Next, flyback with RCD snubber simulation result. This is the simulation that has been constructed in MATLAB. And this is the output waveform that been obtained from the simulation. This is the flyback with RCD snubber result. On the left side, when switching frequency 10 kHz, and the right side, when switching frequency 50 kHz. Next, on the left side, output voltage versus duty cycle. As the duty cycle increase, the output voltage also increase. When switching frequency is 50 kHz, it produces higher output voltage compared when switching frequency is 10 kHz. On the right side is efficiency versus duty cycle. For efficiency, as the duty cycle increase, the efficiency also increase. And when switching frequency 50 kHz, it produces higher efficiency than when switching frequency is 10 kHz. Active clamp flyback simulation result. This is the simulation model for active clamp flyback. Next, this is the output waveform that been obtained. This is the overall result for active clamp flyback simulation. Black table represents switching frequency 10 kHz and blue table represents when switching frequency 50 kHz. Then the graph is plotted. The output voltage versus duty cycle. As the duty cycle increase, the output voltage also increase. In active clamp cases, when the switching frequency is 50 kHz, it produces slightly higher output voltage, almost similar with switching frequency 10 kHz. Same goes to the efficiency. As the duty cycle increase, the efficiency also increase. When switching frequency 50 kHz, it produces slightly higher efficiency than 10 kHz. Lastly, interleave flyback simulation result. This is the simulation that has been constructed in MATLAB. This is the produced output waveform. Result for interleave flyback simulation for switching frequency 10 kHz and switching frequency 50 kHz. When the graph is plotted, you can see that when the duty cycle increase, the output voltage also increase. Same goes to the efficiency. As the duty cycle increase, the efficiency also increase. And when switching frequency is 50 kHz, it produces higher output voltage and higher efficiency compared to when switching frequency is 10 kHz. Now, comparison between all four types of flyback converter. In terms of output voltage, when switching frequency 10 kHz, interleaf flyback produce highest output voltage, followed by active clamp, RCD snubber, and conventional flyback converter. When switching frequency 50 kHz, interleaf produce highest output voltage, followed by active clamp, conventional flyback, and RCD snubber. The best topologies in terms of output voltage is interleaf flyback, as it produces the highest output voltage for both switching frequency 50 kHz and 10 kHz. Comparison in terms of efficiency. When switching frequency 10 kHz, active clamp has the highest efficiency, followed by RCD snubber, conventional, and lastly interleaf. When switching frequency 50 kHz, active clamp has the highest efficiency, and the other three have similar efficiency. In terms of efficiency or converter performance, active clamp is the most efficient flyback converter. On the other hand, interleaf flyback is the worst in terms of the efficiency, despite it has the highest output voltage. In a conclusion, with various duty cycles that have been simulated, the duty cycle equal to 80% produce the highest output voltage as well as the efficiency. Also, when the switching frequency is higher, the output voltage and efficiency is also higher. Second, interleaf flyback converter produce the highest output voltage, but the lowest in terms of efficiency due to high input current. Lastly, active clamp flyback can be considered as the most efficient flyback, as both output voltage and efficiency are high. With that, I conclude my FYP project video. Thank you.